Hey everyone, Nishant here. Today I'll be going over Examprep discussion 9, question 2, to do with binary trees and coding with binary trees. So here we have the following tree class, and this tree class has various, or the constructor for the tree class is here, where we have a left, a right, and a value. Very similar to when working with linked lists. We had a value and a right pointer, or a next pointer and a previous pointer. If it's a double linked list, similarly, we have a left and right pointer. So we can construct something where there's a root and then use left and right pointers to get to the next tree. So it's this sort of structure here. So this is the class we'll use, and we'll be using these various methods within the methods that or functions that we want to implement. Okay, so let's start with 2a. 2a, what we have is given a binary tree, we want to check if it is a sum tree or not. Essentially, what a sum tree is that the value at every single non-leaf node is equal to the sum of its children. When we say the sum of its children, we're just saying the two or one immediate children of that root. What this means is we are sort of ignoring the leaves when we don't need to check if they are equal to any sum. So if we're gonna manually check this sum tree or this tree to see if it was a sum tree, what we would do is say, hey, we can start at 30 and then go, okay, is 30 equal to 9 plus 21, right? It's two immediate children, and that's correct. Then let's just say 9 is 9 equal to its child 9. Yep. Then 21 is 21 equal to its two children 15 and 6. Yep. And then is 15 equal to its two children 7 and 8. So what we didn't do is check 9, 7, 8, or 6 because those are leaves. So that's something we have to account for in our when we're doing this question. And we also noticed that for 9, we counted one of the children, but there wasn't another child. But we still had, we're still able to match this up. So that's a few things we should think about. Now let's try, jumping into this question, see how we can code it up. So the first thing, whenever we're doing some of these problems, well, we want to think about, okay, are we doing this recursively or iteratively? In this case, we'll go with the recursive approach. It's much easier to do a lot of these tree problems recursively, as you'll see. And if we're doing a recursive approach, we should have base cases. And this is very important, right? If we have a base case, and our bases are incorrect, or we're doing recursion, our base case is incorrect, we're going to have infinite recursion, or in some cases, just incorrect code. So let's first tackle those base cases. And what the base cases are, if we're starting at the root, the base cases are situations where we need to return true because there is nothing that we're going to check the sum of, right? So what we can imagine is at all these leaves, they don't have left or right children. So their left or right children are null. That's one piece. And the other piece is that notice that when we're making recursive calls, we're going to make recursive calls on both children of any node, right? And we'll get to that when we have the actual recursive case. But let's look at this one situation here. When we make a recursive call here, and we say, hey, left, let's call this function on the left, let's call this function on the right. When we go to the right, when we check its children, everything is fine. But when we go to the left and try to check children, we'll have a problem and we'll run into a null pointer exception. So it's always a good idea to check if the thing that was passed in is null to begin with. So with that out of the way, then we can do, the checks of the children. So this will be t dot left child equals null. And remember that both of the children should be null, because if we only chose one null child, or we checked if it was like an or case, we would we would be unable to kind of traverse this part of the tree. Yeah, so in that case, we'll have to do an and then check in, see if the right child is null. Okay, if this is the case, let's return true. And the reason we're returning true is that this isn't a situation where these situations are not places where we would not have a sum tree, right? Because there's nothing to check here. They're all leaf nodes or like a non-existent node. Okay, so then when we go into the next part, and we look at sort of how do we check these values, we should keep in mind the same situation, right? We still don't want to run into any null pointer exceptions. And in any cases where we don't have both children, we don't want to have this issue. Since that's the case, we should always check to see if something is null before assigning a value. And if we have to check if it's null, we should then keep some variable that is initialized as 0. So if something is null, let's say in this case, the left child is null. The left sort of variable would be 0, and we could sum together left plus right. So I'm going to declare here, right, I'm going to declare integer left, right, to represent the two integers on the left and right. And remember in Java, when we initialize integers, or declare integers rather, they're already set to 0. So here we have left and right integers already set to 0. And we can just perform the null checks and assign them to their correct values. So if t dot left child is null, or rather is not null, then let's assign left equal to t dot left child. And in the case that t dot right, or that the right child was null, we should catch that. Otherwise, let's have the right variable represent t dot right child. Always good to have these null checks in your code. In the case that these both have non-null values, we'll assign the values to right and left. And then it's for a recursive call. One case we should check, right, at the very node that we're checking, we should make sure that the left and the right children have the same values, right? So remember back here, we said, okay, does 9 and 21 have the same values? And that was the whole situation that we did here. So we see if t dot value is equal to left plus right. And what we want to do is make sure that the entire tree is a sum tree, right? So we need to make the two recursive calls to the left and right children. And hopefully, well, ideally all of our logic in the base cases and in this body here handle these calls correctly. So we'll make a call to the sum tree on the left child And let's make a call to some tree on. Cool. So this is implementation for the problem. And if we do track to see what is going on here, it's going to follow pretty much the same algorithm or that we used like just to check this by hand. These null checks make sure that we're not running to null pointer exceptions. We already have left and right initialized to 0 by default. So that would factor into this check. And we'll make all the recursive calls, and eventually everything bubbles back up to this final statement, because stuff would return true here if we reached like all the way to the end of the tree, a leaf, or we would return false at this statement if there was ever any situation where one node was not equal to the sum of its children. Okay, now for part B. For part B, we've been given a binary tree with distinct parts, an input list, and an NP output list. So it says we want to add all the elements in the input list to the output list that appear in the tree. So what this entails is, or what we should start thinking about is, okay, we need to have some traversal over the tree so we can see all the elements. And then if this element, some element in the tree was in the input list, we should add it into the output list. So given that, we're given actually a traversal. We have the in-order traversal. So we actually want to traverse this tree in order, and then the output list should be ordered in the same order. So as long as we perform our traversal in order and do the checks, we should have a correct output. So it says, for example, the tree in question 2a, assuming it only has distinct parts, input list is 15, 9, 8, 36. Then after the operation, the output list should be 9, 30, 15, 8, and 6. So this says we're assuming distinct elements. So I'll just, let's just block this one out. And yeah, because that's the only non-distinct element. But what would the in-order traversal be? Generally, the way that we want to, or always the way we want to perform in-order traversals is by visiting left subtree. And this is like a sort of recursive algorithm, but visit the left subtree, go up to the root, visit the right subtree. So the way this would work in practice, or like if we did this by hand, is that we start at the root, we go and visit the left subtree, and this would sort of just be a list of our in-order traversal as we're visiting everything, as you saw in question 1. But we have 9, we go back up to the root, 30, then we visit the right subtree. But when we visit the right subtree, we go all the way down to the left, then up to the root, 15, 15, then off to the right for 8, back up to the root, 21, and then 6. All right, so we have commas just for clarity. So now we have this list here. And this is like the in-order list. And it says if the input list is whatever 15, 9, 8, 30, 6, what should our, like this would be our output list. And here we can just sort of compare everything, right? We go at 9, we say, hey, is 9 in our list? Yes, it is. So we add 9. Then we hit 30. Hey, is 30 in our list? Yep. So we add 30. Then we hit 7. Is 7 in our input list? Nope. Skip 7. Move on to 15. And is 15 in our input list? Yes, it is. Add 15. Now we check 8. Is 8 in our input list? Yes, it is. And finally, then we have 21. 21 isn't in our input list. And finally, we have 6, leaving this as our output list. So that's sort of how we would do this by hand, and sort of inspires how we're going to approach this question. So essentially what we want to do is we have been given an output list already as a parameter, and we're going to modify that in place, right? Just add elements to it. We can assume it was empty. And then our input list never changes. The only thing that should change is what we're looking at in the instance of the tree. So with that in mind, we should first handle sort of the general base case, right? Whenever we're doing the traversal, and we're going to start like doing traversals on the left side, or sort of like making recursive calls on the left side, we're always going to hit like some null case. And then when we hit a null case, we sort of don't want to do anything, right? There's no return statement here. We don't really want to do anything. We just kind of want to close that stack frame, move on to the next recursive call. So let's do this. If t is null, let's just do nothing. Or rather, if t is not null, let's do some stuff. And then if t is null, let's do nothing. Okay, so how are we going to achieve this sort of, traverse of the left subtree first, then root, then right subtree? And the way we do that is making the calls to all the left children first as much as we can. We hit the null cases, we'll sort of come back up, do certain checks to make sure to see if we can add into the output list. And then we'll do all this stuff for the right children. In this way, we'll go in a post or in an in-order traversal. So if we make a call to sort relative with t dot left child input list output list, what we can imagine is we're making a recursive call directly here on 9, and that will be the first thing that will enter this check right here. And this is where we want to then check if the input list contains the value that we care about. And if it does, we can just add it to the output list. Right. So what we're doing is we're looking at the left children first, and that will allow us to sort of always go to the left subtree. So if we go back to the example, we'll do this, we'll add the value, make the call back, hit 30, check for that value. Then what do we do, right? We need to have some way to go to the right tree. And if there's ever a time where the right tree is null, then our if condition would catch it. So that's when we actually go to the right. Right after traversing the left, go to the right. Okay, so what does that do? When we go to the right tree, assuming we've already hit 9 and 30, we're going to go to 21, and 21 makes a call to 15, or the node that has 15, and that makes a call to 7 first. And so we're always going to follow this order of looking at the right child after we've looked at the left child and looked at the root. And so this order of recursive calls follows the in-order traversal of the tree. And then in between, we're always checking to see if this value can ever be added to our output list based on the input list, which never changes. And the output list does change, but is added to or just appended to sort of with each recursive call in that order. Yeah, that's about it. Thanks for listening and have a good one.